Kerr effects. Nonlinear effects, which can be readily described by the intensity dependent refractive index of the fiber, are commonly referred to as Kerr nonlinearities. At low intensities, the polarization is a linear function of applied electric field, and hence the resulting perturbation of the field can be realistically described by a constant refractive index. But at higher optical intensities, the perturbations do not remain linear function of the applied field, and Kerr nonlinear effects may be observed. There are primarily three processes which produce Kerr effect, like that we have said, that self phase modulation or SPM, cross phase modulation, and four wave mixing. The intensity dependent refractive index causes an intensity dependent phase shift in the fiber. Hence, for a light pulse propagating in the fiber, Kerr nonlinearities result in a different transmission phase for the peak of the pulse compared with the leading and trailing pulse edges. This effect, which is known as self-phase modulation, causes modification to the pulse spectrum. As the instantaneous frequency of a wave is a time derivative of its phase, then a time varying phase creates a time varying frequency. Thus, self phase modulation can alter and broaden the frequency spectrum of the pulse. The spectral broadening caused by self phase modulation produces dispersion like effect, which can limit the transmission rates in some long haul optical communication system depending on the fiber type and its chromatic dispersion characteristics. For ultra short pulses, like less than picosecond width, with very high peak powers, its effect can be very strong, generating a broad continuum of wavelengths. Although self-phase modulation can simply be used for wavelength or frequency shifting, it has found major application for pulse compression within single mode fiber transmission. In this context, self-phase modulation effectively imposes a sharp or positive frequency sweep on the pulse. This phenomenon, combined with the group velocity dispersion occurring within the fiber, allows optical pulses to be compressed by employing like a pair of diffraction grating, in which the longer wavelength light traveling at the front of the pulse following a longer path length than the shorter wavelength light at the rear of the pulse. Hence, the rear of the pulse catches up with the front of the pulse and compression occurs. Furthermore, for critical pulse shape and at high optical power levels, such pulse compression can be obtained in the fiber itself, which form the basis of so-called soliton propagation. Cross-phase modulation or XPM is a similar effect to SPM, except that overlapping but distinguishable pulses processing, for example, different wavelengths or polarization, are involved. In this case, variations in intensity of one pulse will modulate the refractive index of the fiber, which causes phase modulation of the overlapping pulses. As with self-phase modulation, this phase modulation translates into frequency modulation, which broadens the pulse spectrum. Thus, cross-phase modulation is exhibited as a crosstalk mechanism between channels when either intensity modulation is used in dispersive optical fiber transmission, or alternatively when phase encoding is employed. Moreover, the strength of the cross-phase modulation increases with the number of channels, and it also becomes stronger as the channel spacing is made smaller. There is no energy transfer, however, between channels, which distinguishes the effect from other crosstalk processes in which the increase in signal power in a channel takes place only by a reduction in power in another one. Although the overall strength of cross-phase modulation is twice that of self-phase modulation, because the total intensity is the square of the sum of two electric field amplitudes, the effect is weakened as pulses with Different wavelengths or polarizations are usually not group velocity matched, and therefore the overlap is not maintained. The beating between light at different frequencies or wavelengths in multi-channel fiber transmission causes phase modulation of the channel, and hence the generation of modulation sidebands at new frequencies, which are termed four-wave mixing or FWM. When three wave components co-propagate at angular frequencies omega 1, omega 2 and omega 3, then a new wave is generated at frequency omega 4, where omega 4 equal to omega 1 plus omega 2 minus omega 3. This frequency combination can be problematic for multi-channel optical communication, as they can become phase matched if the channel wavelengths are close to the zero dispersion wavelength. Four-wave mixing is therefore one of the broad class of harmonic mixing or harmonic generation processes in which two or more waves combine to generate waves at a different frequency, that is the sum or difference of the signals that are mixed. Such second harmonic generation or frequency doubling is common in optics. It combines two waves at the same frequency to generate a wave at twice the frequency, or equivalently the half the wavelength. This phenomena can occur in optical fibers, but the first harmonic of the 1.55 micrometer wavelength is at 0.775 micrometer, which is not quite in the optical communications band, and thus it does not interfere with the signal transmission wavelength. Although four-wave mixing is a weak effect, it can accumulate when multi-channel signals remains in phase with each other over a long transmission distance, which is typically when the fiber chromatic dispersion is very close to zero. Hence, pulses transmitted over different optical channels at different wavelengths stay in the same relative positions among the fiber length because the signals experience near zero dispersion. In this case, the effect of four-wave mixing is amplified and a noise signal builds up in which interferes with other channels on the system. Hence, one method to minimize crosstalk resulting from four-wave mixing in wavelength division multiplexing system based on low dispersion fiber is to employ unequal channel spacing, so that the four-wave mixing noise uh, components are not generated at frequencies which correspond to the channel frequencies.